All right, chapter 7 for exam 5 is on the combined topic of atomic structure and periodicity. I have to explain what that means, but they're a perfect match. And I think you'll see as we proceed why there's such a good fit between the two. In fact, atomic structure explains periodicity. Periodicity is a term we use for a characteristic, one of the characteristics of elements in the periodic table. That's why it's called a periodic table, but we'll get to that in a couple of minutes. So let's see. We're recording, and I want to make sure my video is pinned. Yeah. So that when I publish this thing on YouTube, that the world can't see who my students are. I'm trying to protect your identity. Okay. So I need to share and PowerPoint slides. There we go. Let's start the slideshow. Come on. There we go. Okay. Let me move some of this stuff to the side so I can see what's going on. There's Ms. Norman. Let's see. There we go. All right. So this is sort of an introduction to atomic structure. Everybody loves fireworks. I don't know anybody that doesn't like fireworks. But only the really curious are wondering why the fireworks are those colors. Some just accept the colors and go home happy. But some of us really want to know why the colors are there and how to produce those colors. And some of the people that know that magic or create the fireworks. The colors of fireworks, and actually colors in general, as it relates to chemistry, have been known for centuries. But they were produced more by way of recipe rather than understanding of the underlying chemistry. It's only in the modern age that we started to find out why things change colors, why they produce colors under certain circumstances, and how we can control that. That's why we have clothes that are just rainbows of colors if you want them. That's a modern phenomenon. Okay, so the questions that we consider when we're trying to discern the nature of color and why certain chemicals produce colors and others don't, or produce different colors, is we want to know why the colors are there to begin with. What's the underlying cause of the colors? Then we can ask ourselves, why do different chemicals produce different colors? And this is just an example. You have these different elements. There's barium, produces kind of a deep dark blue color in a flame, that is. And potassium produces kind of a hot pink. Sodium is more orangish. Calcium is a little yellower than sodium. And zinc is a bright yellow. And those are just a handful. Strontium produces a color that's similar to potassium. And we might wonder why, because they're not in the same group. So these are just questions to ponder. We also wonder why different chemicals yield different colors when they're treated differently. If you put a chemical in a flame, it may produce one color, but if you dissolve it in water, it may be a completely different color. Why do some chemicals produce the same colors? Right? That's the flip side of that coin. Some chemicals do produce the same colors. For instance, oxygenated blood. We know that's red, right? Now we know the red color comes from oxyhemoglobin. That is the hemoglobin that's oxygenated in your arteries, coming from your lungs, going to the rest of the body. And now we know that that's due to the combination of oxygen and iron in the hemoglobin. But you can also get a red color that looks similar to that from the shells of crawfish. And I did my master's research on processing waste from crawfish plants in Louisiana. And we extracted the product of the processing of crawfish for commercial sale and discovered that the primary pigment in their shells is a compound called astaxanthin. It's a carotenoid, which probably doesn't mean anything to you, but carotene, think of carrots. Right? It's in that family. But notice that whereas oxyhemoglobin has iron in it, astaxanthin has no metals at all. So how can it produce the same color as oxyhemoglobin? Well, it produces the same color to our eyes. That's key. When you have the instrumentation that can analyze those colors, you see that there are significant differences between them. And that's spectral analysis. But the color in astaxanthin is produced by a completely different mechanism. And you see, I'll just draw your attention. Let's see, where's my pointer? I'll draw your attention to all these double bonds. See, there's a double bond, there's a double, there's a double. And the double bonds occur every other bond. So there's a single, there's a double, single, double, single. Those series of bonds are what we say are called them conjugated. And when they do that, it produces a certain shift in their absorption spectrum. The light that they can absorb and the light that they emit. So I won't say any more about that. I could spend 2 or 3 days on it. Okay, so the answer really to why the colors are produced has to do with electromagnetic radiation, that is light. What's the nature of light and how does light interact with matter, or how can matter produce light? Well, we have to characterize light first. We need to know something specific about light itself. So now we're talking about physics, which is unavoidable. But physicists are kind of stuck over here in their cubbyhole, and chemists, they draw from all over the place. We're jacks of all trade, chemists are. Okay, 3 characteristics of light that define it. One is the wavelength. Right? And in order for that to make sense, you have to say, well, if it's got a wavelength, then light must be a wave, right? So we represent light as a wave. Something like that. Well, a wavelength is the distance between 2 crests or 2 troughs or any 2 points on the wave that represent the beginning of a new cycle. So we usually start with a crest. It's easier to identify. So you go from here to here. That's a wavelength. And we represent that with the Greek letter lambda. That's a small Greek letter lambda. And of course, in the SI system, the wavelength is in meters. That's the standard unit of anything in the SI system is meters. Frequency. Frequency and wavelength are related. That same wave we can talk of in terms of frequency by observing what happens as we stare at one point. So if we stare at this point, right, we look at that point, then we see how many crests pass our vision in a second. That's frequency. How many waves, actually, how many waves pass a point in 1 second? And that's, it used to be called just cycles per second. And in reality, it still is cycles per second. But cycles is a non-dimension. Right? It really doesn't have a definition, except that same thing comes by every second. So when you see frequency, which we give, it's represented by a symbol nu, which is a Greek letter. Kind of looks like a weird V. We see that the units there are reciprocal seconds, right? Because this is in the denominator. But since cycles doesn't mean anything, they always include reciprocal seconds. That's it. But we also are honoring a scientist called, his last name is Hertz. So this also equals to Hertz. 1 reciprocal second is 1 Hertz. And you need to know that if you need to do a calculation, because like I've said many times before, if the calculation uses a peculiar unit of measure that you don't find anywhere else in the dimensional analysis, then you can't cancel it. But if you understand Hertz means reciprocal seconds, then you may be able to cancel and come out with a reasonable resolution or an answer. So that's wavelength, frequency, speed. Okay, what's the speed of the wave? Well, the speed of the wave is, I'll have to draw it again. The speed of the wave is how long does it take that particular crest to get from here to there? So that would be meters per second. Right? Meters is the standard unit, second is the time unit, meters per second. So it goes, this one goes how far? So many meters in 1 second. And it's very fast, right? In a vacuum, light will travel almost, well, 10 to the 8th meters in 1 second. Okay, so it's really fast. Actually, light has different speeds. This is in a vacuum. If it travels through anything else, matter that allows it to travel from one place to another, it's not opaque, then the speed is different and always slower. Vacuum is as fast as light's going to get. Okay, so, and these three terms are related. So the speed of light is equal to its wavelength times its frequency. Okay? So just check the units, right? Speed of light should be meters per second, right? Meters per second. Lambda is meters, right? Frequency is reciprocal seconds. Didn't we say that? So there it is on the bottom. Meters per second. So when you multiply those two together, you get this. So what kind of relationship is that? If the speed of light is a constant, and it is for a vacuum, and we can treat it as a constant, at least under these circumstances, then what have I said about, well, think of Boyle's law. Pressure times volume equals a constant. What kind of relationship is that? It's inverse, right? As this one goes up, that one has to go down to keep this one constant. Same thing. As the wavelength goes up, frequency has to go down to keep that constant to C. So it's an inverse relationship. And in fact, this relationship can be used, this type of relationship can be used for any type of wave. All you need to know is the speed of the wave and maybe its wavelength, and you can find out what its frequency is. You can do it with sound, right? How fast does sound travel? Well, it depends, but let's see, in ballpark, 1,000 meters per second. That's a big ballpark because I can't remember the exact value. But you can substitute there the speed of sound. And then once you have one of these known, then you can find out what the other is. Or if you know these two, you can find out what the speed of sound is for that particular experiment. So this is nothing peculiar. The only peculiar thing to light with this formula is that speed. Light is the fastest known thing, not thing, the fastest known, well, yeah, it is a thing. It's the fastest known phenomenon in the universe, speed of light. And in fact, with our current technology and the way we understand physics, the speed of light is a barrier. Nothing can go faster than the speed of light as it travels through space. Now, there are various theories that are proposed for exceeding the speed of light, but in order to do that, you've got to actually take space with you. Right? You can't go through space, you take space with you, and you sort of ride a wave. Thus, Star Trek, the warp drive. Okay. So we have a formula. If we know any two of these variables, the constant and a variable, we can find the other variable. Or if we have the two variables, we can find out what the constant is. So if we can determine the lambda and nu in a different substance, for instance, diamond, then we can calculate the speed of light through diamond, which is much, much slower than it is through a vacuum. Okay, so this is just an illustration of something that what I've been talking about already. This is a wavelength, and you notice that these wavelengths get shorter and shorter for these three different types of light. So as the wavelength gets shorter, what happens to the frequency? 4, 8, 16, as the wavelength gets shorter. That just illustrates the inverse proportion that that is the formula, no, the equation, excuse me, the equation that we just discussed. Okay, now we can also characterize, and we need to understand, define regions of the electromagnetic spectrum, we call it. So you can have a wavelength, and the wavelength can get big, 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 or it can get really, really, really small. Or as it gets smaller, frequency goes up. It gets really, really big, or to the right, when the wavelength gets long, it gets really, really small. And we have subdivided the electromagnetic spectrum into regions. And we use these regions for various purposes, depending on the nature of the light and how matter interacts with it. Right? It's not just the light itself. The visible part of the spectrum that we respond to in our retinas is very narrow, right? See, it's 4 times 10 to the minus 7th up to 7 times 10 to the minus 7th, and those are estimates of meters wavelength. So it's very narrow. Now, if the wavelength gets longer, that is to the right in this spectrum, as it gets longer, then your first region you encounter is infrared. And we often associate infrared with heat. Right? When your food is prepared at a restaurant, they stick it under heat lamps. And the heat lamps are designed to emit infrared radiation. Let's see, did I miss somebody? 10?
Dr. Bly, I'm on my phone and I accidentally hit my power button and it completely took me out of Zoom. I had to log back in.
Oh, okay, okay.
I'm sorry.
that explains it. Okay, so as the wavelength gets longer, we move to the right in this representation. Here it is, wavelength in the meters. It's longer to the right. We come to infrared. Wavelength gets even longer. We come to microwaves. Right? We use those to heat food also. We use them for communication as well. But in our kitchen, we use a certain frequency of microwave energy, which is particularly exciting to water molecules. In other words, the wavelength of that microwave in your oven is what we call resonant with water. So water likes that frequency. It starts to vibrate violently. So something inside the molecule responds to that radiation. And as it vibrates, it releases that energy that's delivered to it through the microwaves to the surrounding water molecules and the other molecules of your food and heats it up from the inside out. The next region we come to is radio waves. And they can be very, very long. Like they can be, one wave can be several miles long. The shorter end of that spectrum we use for FM. The longest end we use for AM. And the reason, I don't know if any of you have, we don't do it much anymore because we have the internet, but we used to sit up at night and tune in our AM radios to, and at that time I lived in Tennessee and then in Georgia. We used to tune into radio stations out of Chicago. You couldn't get them during the day, but you can get them at night when there's not, it's interference from the sun, which produces lots of these different wavelengths. But you could also get them because the ionosphere, the upper regions of the Earth's atmosphere, is ionized, and it produces a layer that will reflect waves of that wavelength, the AM band. So you could get, in fact, shortwave does it too. Right? If you know anybody that's a shortwave enthusiast, they communicate with people that are on the other side of the globe, simply because those waves go up and they bounce between layers inside the ionosphere. And once they get, they don't know where you are, so they leak as they go. And you can pick up, as a shortwave operator, you can pick up those signals from the other side of the globe. Okay, so we go the other direction where the wavelengths get really short and the frequencies go sky high. First thing you come to is ultraviolet. And of course, ultraviolet has its subdivisions, regions, right? We have for protection from sunburn, you have two basic regions, UVA and UVB. And the chemicals that are put in sunscreen are tailored to absorb various regions of the ultraviolet so that they don't damage your skin cells. Because that's what a tan is. It's your body's response to sun damage. Okay, so we get shorter wavelengths, we get into the X-rays, right? And they can penetrate right through your body until they get to bone, and bone tends to absorb X-rays. So that's why you can take an X-ray picture of a limb, say, and find a break. And then you can get really, really, really short wavelengths, and they're extremely high energy, and I'll explain what that means in a minute. But these gamma rays are produced by extremely violent astronomical events, such as the explosion of a star, a supernova. Other types of astronomical events can produce gamma rays, and they can be very dangerous. They tend to be focused. Let's just put it that way. When a phenomenon in space produces a gamma ray burst, it's focused in a direction, usually in opposite directions. And if it happens to be focused in your direction, and your planet is in the way when that gamma ray burst arrives, then it can cook all life on the planet's surface. It can just completely fry everything. So fortunately, because they're focused, the chances of our encountering one are pretty small. Okay, so that's the electromagnetic spectrum. I mentioned earlier that when you microwave your food, you're converting one form of energy into another. Well, this is an example of that. We have electricity. It could be AC or DC, it doesn't matter. But as it flows through the pickle, and the pickle is a conductor, right, because it has acid in it, which dissociates, and you have ions that can move. So the circuit is completed through the pickle, but there is some resistance there. And the electricity that's traveled through the pickle is converted into heat, a large amount of heat, like you'll cook that pickle. But some of it is converted into light, right? It's just an energy transformation from one form into another. Remember, you can't create energy, you can't destroy energy, you can only convert energy. And that's what we're doing with this pickle. Okay, so now we're going to talk about, I mentioned earlier, when we got down into the gamma ray region, that we're talking about very, very high energies. That just means that we can equate the energy of light in some form or fashion, in a formula, to its frequency. Very high frequency radiation has very high energy, and it's related by this formula. Okay, that's Planck's formula. This is Planck's constant. Plonk was a well-known, well-respected, and lauded chemist / physicist. And he was given credit. I'm not sure if he actually invented this, but he was given credit for it. And this constant relates frequency to energy. And energy is in joules, right? That's the standard measure. So, and frequency is in reciprocal seconds. So this constant has to be in joule seconds. Because this one is in reciprocal seconds, that means they can cancel, and that leaves joules. Okay, so that's for the units of measure. Now the value there is something I don't have memorized. That's why I put it in the useful information in the back of your review document. But the fact that we can equate these two is based on a phenomenon of light that we refer to as quanta. Light is quantized. In other words, it occurs in packets. And that packet is given a name. It's called a photon. Certain TV shows and movies have made probably billions of dollars by now with various aspects of what we've been discussing so far, such as the warp drive and quantum torpedoes, right? So these things have their application in popular culture as well as in science. But in science, we want to be precise about our definitions. So this packet, this quantum, that's part of the nature of light, is its value is given by that formula. Right? So if you know the frequency of the light, you can calculate the energy that is contained in that quantum. So if something absorbs that much energy, if it absorbs a quantum of light at that frequency, it will get that many joules of energy. Now, suppose you don't know the frequency. Suppose you know the wavelength, right? So here's all you have to do. We know that this formula is true. Right? See anything in common? Right there. Solve this one for that one. Like that. Right? This one stays over here. Now it's over here. This one goes into the denominator. Now you can substitute this in here, and you get there you go. So if you know the wavelength instead of the frequency, you're not stumped. You have recourse. Okay, so that's what I've explained here. Oh, there's Planck's constant, right? So that number, who would memorize that number? If you didn't use it every day, you just have to look it up. So what does that tell you? Well, with Planck's constant being a very, very small number, if you have a very high frequency, then the high frequency actually is, this is a direct proportion, because the constant is over here on this side with that variable. If we put the constant over on this side, leave it there, and put the variable over here with energy, then the constant is equal to a quotient. And anytime a constant is equal to a quotient, you have a direct proportion, a direct relationship. So as the energy goes up, the frequency goes up, or vice versa. As the frequency goes up, the energy goes up. And this proportionality constant, we often call them, is the way that we associate that frequency with that particular energy.
The photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
Okay. You may feel like you just got mental whiplash. You know, why did we just all of a sudden introduce photoelectric effect? Well, actually, photoelectric effect explains the relationship between matter and light. I shouldn't say explains. It sort of does. It gives us clues as to what's happening when light and matter interact. Okay, so the photoelectric effect was Let's see, do I have a slide on that? No. The photoelectric effect was known throughout the 19th century. But it wasn't until the early 20th century when Albert Einstein got hold of the concept. He was still working in the patent office in Bern, Switzerland. And on the side, he was doing theoretical physics. And he explained mathematically the physical phenomenon of photoelectric effect. He published it and later on was awarded a Nobel Prize for that paper. So most people think of Einstein as famous for E = mc squared, which he is, of course, but he got his Nobel Prize for the photoelectric effect. So what does the photoelectric effect mean? Well, recall from that video that light of a long wavelength toward the red end or longer would not produce a current. That is, it would not eject electrons from the surface of the metal. It's not enough energy, right? So when you move to the blue end of the spectrum and start increasing the frequency, increasing the energy, decreasing the wavelength, which is increasing the frequency, you increase the energy. Now there's enough energy to eject electrons from the surface of the metal. So what that says, basically, is that electrons respond to light. When light strikes matter, electrons in the atoms respond by absorbing the light and doing something about it. If there's enough energy in the light, when the electron absorbs it, it will leave the atoms or in its neighborhood completely. Just leave the surface. That's why you can detect a current with the photoelectric effect. Now, anything less than that, they can still absorb the light, right? And they move within the atom when they do that. And we'll explain that later. In fact, this is going to take 2 class periods to get this one done. So, the photoelectric effect was a clue to the interaction of light and matter, and why matter can produce light in fireworks, for instance. Now, we're going to digress for a second. E = mc squared, energy has mass, right? So what does that mean? Well, we've been talking about light up to this point as a wave. And if you watch waves on the surface of water, and you wad up some paper and throw it out there as a boat passes and it makes waves, then what you'll see is the paper or whatever you throw out there, cork, or if you throw your lure out there and it's got a float at the top, as the wave passes, the float just kind of moves up and down. Doesn't go anywhere, right? So what that tells you is that the matter's not moving, and that it's just the wave that moves. Well, there are other phenomena, including the quantum nature of light and the equating of light with energy and mass, that have stumped scientists for centuries. Some were big wave supporters. They say, no, light is a wave, that's the end of the story. And light was described in terms of waves first. So they sort of had dibs on the territory. But observations of these phenomena that we just described tend to not be explained with waves, right? You can relate them, like the quantum theory relates energy and frequency. But this photoelectric effect, it's as if light has mass, right? You wouldn't expect the electron to move unless something moved it, like two billiard balls, like one ball comes on, hits the other one, and it moves off. So that phenomenon, the photoelectric effect, tends to suggest that light it also has a particulate characteristic. It can be described in terms of waves and as particles. So we call that the dual nature of light. And after arguing for decades, scientists finally just threw up their hands and say, okay, light's both. Right? It has wave and particular properties, okay, which is correct. Both are correct. So this is a case where you restrict the use of the theory. So if your theory is in terms of waves, then there are only certain types of problems that you can solve relative to light using that wave phenomenon. And if you need to solve a different type of problem, then maybe the particulate nature and the equations that go with that one will solve that problem. Never been able to successfully describe light in terms of just one nature. It has both particulate and wave nature. Okay, let's talk about spectra. We described the electromagnetic spectrum as continuous, and we showed that that little picture of the electromagnetic spectrum. And if you observe light from the sun, we say the light from the sun is white light, which is almost true. It's virtually a continuous spectrum, but it does have breaks in it. And you can only see those breaks with the proper instrumentation. You need a spectrograph to spread the light out and show you where those places are. Well, so we have two types of spectrum. A continuous spectrum, and that's generally considered to be white light, because when you pass the light through a prism, then it spreads the light out into its colors, and you don't see any breaks in it. So that would be a continuous spectrum. Then there are line spectra. And these spectra are usually produced by individual elements that we excite and make them glow. And then the light that comes off of those, then we put that through a prism, and it produces discrete lines of color, different colored lines. And our example here is the hydrogen emission spectrum.
White light that is passed through a prism separates into a rainbow or continuous spectrum consisting of colors from violet through red.
Okay, and we can artificially produce white light. We know how to do that. We can produce a continuous spectrum. We don't have to use the light from the sun. We can do it artificially, and it's represented here with this light bulb, but it's probably a very special light bulb. Now the line spectrum is a little bit different.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
Right. The key there is the visible region. We can see those 4 lines at those specific wavelengths for the hydrogen emission spectrum. But it also produces emission lines in the non-visible regions of the spectrum. In fact, I used to use an instrument in the lab where we were, the detector for this instrument, I'll just put it that way, had within it a lamp that was filled with a special isotope of hydrogen. It was deuterium, right? So it had 1 proton one neutron. And that particular isotope emitted light of the wavelength that we needed to detect various compounds that were coming out of our analysis. Okay, so we had that deuterium lamp. We also had another lamp that was tungsten, basically, that produced the visible region wavelengths that we would use for other types of detection. But we needed the ultraviolet region of that deuterium lamp. And it's sort of a hydrogen spectrum, but it's a special one. So, what can we derive from the line spectrum? The line spectrum implies that only certain energies, because remember, the spectrum occurs at different wavelengths, and those wavelengths represent different frequencies, which in turn represent energies. So only certain energies are allowed for the electrons to move from one place to another in an atom. And relative to the nucleus, they can move from a lower, closer place to the atom to a higher place away from the atom and still be part of the atom. They're just excited state. And they will only absorb a certain wavelength of energy, certain energy, to get from one place to the other. If they don't have exactly that energy, then they won't move. Now, going from a lower energy to a higher energy means that they have to absorb energy to go from low to high. But for the line spectrum, what we get is the electron returning to a lower energy state. And when it does that, it gives up its light. And that's what you see as the line spectrum. So this explanation, the quantized movement of electrons within an atom, explains why you get the line spectrum. Okay, and this is just a, so you got it there in print, so to speak, is why I created this slide. It would say the same thing I just said. Okay, so what type of model of the atom would account for this energy absorption and emission? Well, the first attempt of that model, and remember, whenever you hear model in scientific terms, think theory. Models are invoked to help explain why something happens, and that means theory. So the Bohr model of the atom, Niels Bohr was a Danish physicist slash chemist of the early 20th century. And he was in there with all those big brains like Einstein and Plonk and a whole host of others. And he proposed a model for the atom that was basically sort of an extrapolation, not an extrapolation, an interpolation, because it gets smaller, a representation of the atom in terms of the way the planets are arranged, right? The sun would be the nucleus, and each of the planets would be an electron in its orbit. Right? So he proposed, the Bohr model then was, the nucleus is here with its protons and neutrons, and then the electrons orbited that in their discrete orbits, and they didn't exchange. They didn't move from one orbit to the other unless they were forced to by absorption of energy. And he gave each one of these levels a number, right? And it goes up further than that. But that has come to be referred to now with our current understanding of the atomic structure. This is known as the principal quantum number. And it references the energy levels within an atom. So even though Bohr's model is not accepted anymore, in other words, it explains just a few things, but not everything we want to know, we still refer to each of these levels, these energy levels, as the principal quantum number, or the Bohr energy levels. So another restriction that we have to place on the Bohr model is that it only works for the hydrogen atom. So that means we can't even have a neutron in there. And it works for not deuterium, not tritium, but oh shoot, I can't remember the no neutron isotope. It's got a special name. I'll think of it in a minute. But the lowest energy level in the hydrogen atom is number 1, right? That's where the electron is going to be at its lowest energy. The lowest energy is always closest to the nucleus. You have to add energy to electrons to get them to move away from the nucleus because of attraction, right? Electrostatic attraction. It's just as simple as that. And this is called the ground state for the hydrogen atom is 1. The ground state for any other atoms are the ones where you have no excited electrons. And you'll see that as we start to build electronic structure in atoms, that the lowest possible energy levels, that's the ground state for that atom. For hydrogen, the ground state is that one electron is in the first orbital. So what happens? Well, in this representation, based on energy, not physical position in space, but just energy. The energy level here is at this level, and then the second one is a lot farther away from 1 than the others are. So as you go higher in principal quantum numbers, the spacing gets closer and closer together. So where do we see those colors in the line spectrum of the Bohr, of the hydrogen atom? You see them in electronic transitions between higher energy levels, not down to the ground state 1, but for these 3, between 5 and 2, 4 and 2, 3 and 2, and there's another one that they left out. It's probably between 6 and 2. Because if you go from 2 to 1, the energy release there is going to be so high, it will fall outside of the visible region. It'll be ultraviolet. Okay, so here's sort of a representation of what you see for these 3 lines, anyway. And they don't show you the nucleus here. All right, so I need to point that out. This n equals 1, that's this first orbital right here. The nucleus is so small you can't see it. Let's just think of it that way. So those levels of energy, the quantum levels, this is n equals 1, and this is n equals 2. So when the electrons return from an excited state to energy level 2, then they give off these various colors of the line spectrum. Now, we can actually calculate the transition from one energy level to another one. And actually, this equation is derived from a simpler one, where you have actually, and this is, remember, this is for the hydrogen atom only, right? That's our restriction for now. We sort of jumped the gun. I need to stick another slide in here. when you calculate the E, what's the energy of an electron relative to its nucleus? Well, what we need to know is what is the quantum number? What is the energy level number? So if we say it's in energy level 1, then we say this constant value, 178, 10 to the minus 18 times 1 over 1 squared. That would be the energy for that electron in the first energy level. And then if it were in the second energy level, you just take everything down. And then you would say 1 over 2 squared. So, but, okay. Notice the negative sign. The negative sign is there to reference the minimum energy for an electron. It's right close to the nucleus. And if you move up to the second level, you have a smaller negative number. So I know it's kind of weird to think of it that way. But you have a large negative number, and then you move to the next level, and you have a smaller negative number because you're dividing by 4 instead of by 1. So as you move out, then you have a certain energy level here, and then this one will have a smaller negative number because the reference is to the minimum energy is at the first level. And you can eventually add enough energy to where the electron leaves the atom. And when you get to that point, the energy content relative to the nucleus of that atom is 0. So our negatives are getting smaller and smaller and smaller until they disappear. And then energy is 0. So at infinity, E equals 0. Okay, I said all that to try to help explain that in order to determine what's the energy of transition from one energy level to another, we would take, if we went from this one to this one, you would have final minus initial. So if this is initial, then it would be on the right over here, and it would make it a positive number. And then that would be combined with this negative number for, say, the first level. And then the transition would be a negative number. And then we take that value and multiply it by this negative constant. And that would make the energy positive. And in order to be positive, well, it just keeps you from having to deal with negative numbers. The positive means that the energy is being released by the atom. Now, I know that runs counter to our thermochemistry standards, where if it was positive, you'd actually be adding energy to it. But in this case, if you go from the second level to the first level, it's giving up energy. So we sort of have to shift our thinking a little bit. But that's why you have these two values, because you're subtracting this one from that one. And what we've done is we've factored out the common element, which is this constant. Right? So the constant would have been multiplied by this one, and then subtract this one multiplied by the same constant. You can factor it out. It's just math. So that's why we have these two here inside the parentheses and the constant sitting out here by itself. Okay? So it's important to place the initial and final in the proper place. If you've got to transition from a higher energy level to a lower energy level, the lower energy is going to be the final here. If you're absorbing energy and going from a lower to a higher, then the higher energy level value will be here and the lower here. And you get a negative number then, which means there was energy absorbed by the atom. Okay, so here's just an example. If we transition, the hydrogen atom transitions from, from 5 to 2, which one of those lines does that represent? It turns out to be blue light at a wavelength of 434 nanometers. All right, so we've got a lot of things in here that I need to explain. Blue light, right? Blue light we know is on the lower end or the higher frequency of a visible range, so that's fairly easy to explain. But where did I get nanometers? Right? Didn't we just say that the standard measurement is meters? Well, scientists like convenience too, and it's more convenient to use a unit of measure that gives you a whole number when possible, right? Rather than a scientific notation that you have to carry around in your head. So 434 nanometers can be converted to meters. You just need to know what's the conversion. Right? Nanometers to meters. So how many nanometers in a meter? Or the converse, how many meters in a nanometer? Ten to the minus ninth meter is a nanometer, right? A billionth of a meter is a nanometer. And there you have 434 times 10 to the minus 9 meters. And then we can convert that, if you want, to scientific notation. Okay? So that's all there is to that. Nanometer is a term that most chemists and physicists, scientists for that matter, understand. They have a feeling for a nanometer. It's very small, for one thing. But what we do is we plug in, if we're going from 5 to 2, it's going to give off light, right? So the final is 2, right? 2 squared, and the initial is 5 squared. Right? So you just resolve this times that, and you get this value. Right? So how do we know that that number of joules is 434 nanometers? Well, you can either take that number of joules and convert it to frequency, or better yet, there you go. So you plug in the energy, plug in Planck's constant, plug in the speed of light, and solve for wavelength. And the wavelength will be 434 nanometers, or 4.34 times 10 to the minus 7th meters. In this blue box, I did it the other way around. I said, how much energy is represented by 434 nanometers? Right? So I went the other direction and solved it for joules. And joules here is within, you know, a hundredth of a joule. Well, a hundredth times 10 to the minus 19th joule. Within 3 significant figures, they're pretty close. Okay, what is it that's good about the model, Bohr's model? Well, the model correctly fits the quantized energy levels of the hydrogen atom and postulates that only certain levels in this circular orbit are permitted. And the physical evidence supports that. Right? So in the beginning, the Bohr model was a good representation. It answered questions. And as the electron becomes more tightly bound, our convention is its energy becomes more negative because it's getting closer to the nucleus. And we use infinity, that is the free electron away from the atom, as our zero energy level. Okay. Let's see, I got 3 minutes. Let me see if I got a good break point in here. Okay. We're just about finished with the Bohr model. I may mention the Heisenberg principle so we can get it out of the way. So let's do that. The fact of the matter is that the Bohr model is not correct. One of the clues is that it only works for hydrogen because it's been tried on other elements. Helium, for instance. All you have to do is go to helium with 2 protons and 2 electrons, and you find out that the model does not work. Under what circumstances will the model work? Well, the model actually does work if we take other elements and make them look like the Bohr atom, the hydrogen atom. So if we take helium, see, I need some more room here. If we take helium, which has 2 electrons, then we ionize it. We take away 1 electron. So the helium plus 1 ion will behave similarly to a hydrogen atom because it only has 1 electron. But we also have to take into account the number of protons. And we do that with our energy formula. We had that constant in here, right? And we had 1 over n squared. Well, now it becomes the number of protons. So you put the number of protons in there instead of the 1. And then for the, what's the term they use? The hydrogen atom analog for each element will give you the same results. As long as you only have 1 electron out there, then it will work. Okay, so we can do calculations for each one of these. We did the blue already. The 4 to 2 is the green one. The 3 to 2 is the orange one. And there's one other one that the creators of this slide left out. Which transition represents the longest wavelength of light? Well, the longest wavelength is right there. No, right here, excuse me. The longest wavelength is represented by the narrowest transition because long wavelength means lower energy. Now, a word about Heisenberg. Heisenberg was another one of those big brains in the beginning of the 20th century. And what Heisenberg said was, there is a limitation, a fundamental limitation that cannot be abrogated in any way to observations of very small phenomena. So what he means by that is that when you get really small, the simple act of observing the phenomenon changes it. Now, when you get to be big, like the size of a human, you can observe the human, and the Heisenberg effect is negligible. It's still there. It's just so small for large masses that the observation has no impact. But when you get down really small, that's what that formula means. It's actually, you cannot know both the momentum, which includes the velocity and the mass, the momentum of a particle, and its position. You cannot know with any degree of accuracy one without losing part of the other one. That's basically the Heisenberg uncertainty principle. And the reason we're introducing that concept is because when you start looking at things as small as an atom, your observations are questionable, right? They're really not accurate. So what we have to do is deal with large collections of atoms and use statistical analysis, probability. So that's where we jump from here to the quantum model, the quantum mechanical model of the atom, which is basically a statistical probability of, well, the electrons are going to be found in this region of space around the atom maybe 99% of the time. But there's a 1% chance the electron might be over here somewhere. Okay, that's what probability means. You can't ever say with certainty. Okay, so we'll pick it up here with I'll probably come back to the Heisenberg and do a little overlap, and then we'll finish out the chapter on Tuesday.